So the reason that this is important and why we need to understand how to calculate areas under the curve in these distributions, or the reason that we need to understand how probability distributions work, is because a lot of the test statistics that we calculate in this class, such as the z-stat that we introduced last week, have a distribution. So this standard normal distribution is the z distribution, which means when we calculate a z statistic, we can estimate the probability of obtaining that z statistic based upon this distribution. So this is important because we're using these statistics to try to draw conclusions about our groups. So last week we talked about a scenario in which we have a binomial data set. Our binomial data set is of course made out of zeros and ones. And we use it to test a hypothesis. So what is our hypothesis? Well, first and foremost is going to be our alternative hypothesis, which is essentially what you really ideally want to know, which is, does our proportion differ from some sort of value, right? So we want to know if the probability of, let's say, being born male is truly 0.5. And we think that there's actually a higher probability of being born female than male because of science. And our alternative hypothesis would be then that the proportion of babies born female will not equal 0.5. We think it'll either be bigger than 0.5 or smaller than 0.5. So the alternative hypothesis is actually what we really generally want to know about. It's what we want to test. But the way statistics are set up, we actually test something called the null hypothesis. And the null hypothesis predicts the opposite of the alternative hypothesis. And what that means is it predicts no difference. So that means it predicts that the probability of being born female would be, 0.5, which is 50%, right? There's two, we could argue this, I argue this all the time, but for simplicity's sake, there's two genders, male, female, and the probability of being born female, we think is actually possibly more likely or less likely than being born male, which is what our alternative hypothesis states. But the null hypothesis says, no, the probability of being born female is 50%, 1 in 2. So in statistics, although we are really interested in the alternative hypothesis, we actually test the null hypothesis. And the reason we do that is because we use our z statistic to calculate a p-value. And what the p-value is it's the probability of obtaining our test statistic, in this case, z, given that the null hypothesis is true. So if we calculate a z statistic, this statistic is going to basically calculate how close to our hypothesized value our proportion is. And that's why when we calculate the z statistic, it actually asks us to plug in the different proportions. So what that tells us is that basically if our z statistic is close to 0, close to the mean, there's a high probability that we would obtain that z statistic given that the null hypothesis is true, given that the sample proportion is actually equal to 0.5. in this scenario. However, there are instances where we might calculate a very extreme z-score. So let's say we actually get a z-score equal to 3.14. This z-score has a very low probability of occurring in this distribution. And remember, this distribution is z-scores given that the null hypothesis is true. So if our proportion really equals 0.5, obtaining a z-score of 3.14, obtaining a z-score out in one of these extreme tails is very unlikely, but still possible. So that brings us to another point, which is alpha. So alpha, let me grab a different color. Alpha relates to something called type 1 error. It's an error rate. And we actually decide alpha before we conduct our experiment, because we want to say, okay, it is possible under the z distribution to obtain an extreme score even though the null hypothesis is true, which means we might actually have evidence suggesting that the null hypothesis is not true in our experiment, and we have to decide how much of that error in judgment we're going to allow into our experiment. So very commonly what people will do is they'll set an alpha level equal to 0.5, which is 5%. Sometimes people will set the alpha equal to 10%, which your book does. And what that's doing is that's basically saying which extreme values of z are we going to possibly obtain and reach the wrong conclusion. So if we get an extreme value in the tail, it's hard for us to decide if that extreme value is just a fluke because they do occur even with a low probability, or if more likely the extreme values actually represent that this proportion does not equal 0.5. So I'll explain that again. The z distribution assumes that the null hypothesis is true. The z distribution assumes that the proportion is equal to 0.5 in our experiment. In that distribution, even when the null hypothesis is true, it is possible to obtain a large z statistic. It does happen. They are under that curve. But if you look at the probabilities in your book associated with really extreme z statistics, it's pretty low. So let's go ahead and look at 3.14. The probability of pulling that z statistic is 0.00169. So the probability of pulling this z statistic is, I won't write crooked, so the probability of pulling that z statistic or obtaining that z statistic in this distribution is less than 1%. It's actually approaching 0.1%. So the probability of it occurring is not likely. However, it can happen. So what that means is when we pull a z statistic like this, we are basically accepting a small chance that we've made an error, which means that the null hypothesis is actually true and we've just pulled this on a fluke, or that this actually indicates, because our z statistic is so large, that it's actually coming from a different distribution. what's our different distribution? Well, our different distribution is basically what the z-statistics look like when the proportion is bigger than 5. Bigger than, sorry, 1 out of 2. So we have a small portion of values here. Let me label this. So this is what a z-distribution would look like if our null hypothesis was not true. There is a little bit of overlap here because that's where that error is occurring, right? The high values in this tail and the low values of this distribution tail do overlap. So basically, when we get values like this, we're accepting some sort of risk. So we have to decide up front what that error rate is going to be and how much of that risk we're going to allow into our experiment.